What are the chances? You buy a lottery ticket, what are the chances that you're going to be rich for the rest of your life? You walk across a golf course in a stormy day, what are the chances you'll be hit by lightning? You go to Las Vegas and you gamble your life's earnings by betting a red on roulette. What are the chances you're going to be rich? You need to invest for your future and live happily in old age, so you buy certain stocks and bonds. What are the chances that those investments will allow you to live happily for the rest of your days? You have a fever, you have a cough. What are the chances that it's a serious disease rather than something trivial? A hurricane. It's spotted on the Gulf Coast, and it's headed toward New Orleans. What's the chance that it will hit and cause damage? What are the chances that a child who's brought up by a drug addict will become a criminal? What are the chances that when you send out an email advertisement to 10 million people telling them to buy a certain thing, that they'll actually buy any of it? All these examples are real examples of life situations where we're confronted with possibilities whose outcomes we do not know. In fact, I would argue that many or most parts of our lives and the world and trying to understand the world involve situations where we don't know what's going to happen. They involve the uncertain and the unknown. It would be nice to say, well, our challenge in life is to get rid of uncertainty and be in complete control of everything. That is not going to happen. So one of life's real challenges is to deal with the uncertain and the unknown in some sort of an effective way. And that is the realm of probability. Probability accomplishes the really amazing feat of giving a meaningful numerical description of things that we admit we do not know, of the uncertain and the unknown. It gives us information that we actually can act on. For example, when we hear there's an 80% chance of rain, what do? We take an umbrella. Now, of course, if the next day comes and it doesn't rain, what do we say? Well, we say, well, there was a 20% chance it wouldn't rain. That's okay. And if it rains, we say, oh yes, the prediction was right. There was an 80% chance of rain. Probability is a rather subtle kind of a concept because it can come out one way or the other, and still a probabilistic prediction can be viewed as correct. But decisions made on probability have all sorts of ramifications. In the case of the rain, all we risk is getting wet. But in many areas of making decisions on the basis of probability, there are very serious consequences. When we make medical decisions, for example, we are making decisions that are based on probabilities, and yet they have extremely serious consequences, including life and death consequences. In the early days of probability, one of the first examples where probability was out in the public, this was before probability was viewed as a commonplace thing as it is today. But back in the middle of the 1700s, between 1750 and 1770 in Paris, there was a smallpox epidemic. And they had developed a smallpox vaccine. But the inoculations were rather risky. They reckoned that there was a 1 in 200 chance of death from taking the inoculation. But on the other hand, there was a 1 in 7 chance of dying eventually from the disease. So making that kind of decision is a very dramatic question where we're weighing probabilities. And if you took that inoculation and you died immediately from smallpox, did you make the right decision or not? Well, of course, you don't want to be among the 1 in 200 that died from the inoculation. On the other hand, on the basis of probability, it was the right decision. There are many controversies about this kind of thing, and in today's world with lawsuits and all, this would be a very serious kind of an issue to undertake. Well, in many arenas of life, our understanding of the world comes down to understanding processes and outcomes that are probabilistic in nature, that really come about from random chance, that things are happening by randomness alone. And over the last couple of centuries, the scientific descriptions of our world have included increasingly have included probabilistic components in them. For example, in physics, Many aspects of physics, from quantum mechanics to thermodynamics, all of them involve questions of probability. Things we imagine molecules moving randomly around and causing things to happen by the aggregate force of probabilistic occurrences. Quantum mechanics, the same thing. At the very foundations of our knowledge of physics is probability. In biology, genetics and evolution are all based very centrally on random behavior. In fact, in all of these areas, the goal is to make definite, predictable, measurable statements about what's going to happen that are the result of describing random behavior. And in fact, the descriptions of these kinds of probabilistic analyses of random behavior is actually what is involved in scientific descriptions of the world. This is a major paradigm shift in the way science has worked recently, is that, by recently I mean in the last 150 years, is that there's been an increase in the amount and the role of probabilistic and random descriptions as the center of scientific descriptions of the world. So one thing that probability tries to do is to describe random phenomena. It tries to give a specific statement about what we expect when things happen at random. And the reason that it can be effective at doing this is that random happenings are things where the individual outcomes of one trial or one experiment are completely unknown. But if you repeat them many, many times, or you look at them in the aggregate, they have some regularity to them. And so the amazing accomplishment of probability is to put a meaningful numerical number value on the things that we admit we don't know. And I want to give you an example that I think captures this whole idea very clearly. This is a die. It has 6 sides, and if I roll this die, it has an equally likely chance to come out any one of the numbers 1 through 6. So I'll just go ahead and roll it, and I don't know what's going to happen. Okay, it came out a 2. Could have come out 1 to 6. I don't know anything about what could have happened. But let me do a similar experiment, except instead of with just 1 die, I'm going to use 60 dice. So here I have an urn. By the way, in probability, we always talk about picking things from urns. So this is now an urn, for your information. And in it, there are 60 dice. Now, I'm going to take these 60 dice, and I'm going to shake them up and roll all of them. Now, when I rolled 1 die, I didn't know what was going to happen. But I claim, without even looking at this, I'm going to show you that just by randomness alone, I have an expectation that there'll be approximately as many 1s, as 2s, as 3s, as 4s, as 5s, and as 6s. Even though I didn't do anything. You saw me. I just shook them up and rolled them. And so I'm going to take a second here and arrange them neatly so we can count how many 1s, 2s, 3s, 4s, 5s, and 6s there are. Okay, we've now arranged the dice so that we can see exactly how many there are of each of the different numbers. Now, in this case, actually, there's more variation than I usually get in this, but I think maybe we should go along with it to demonstrate that there is variation to expect also. We would not expect each of the numbers to come out exactly 10. That would be a very unusual occurrence. Instead, what we expect is that on average, of course, on average, they'll certainly be 10 because there are 60 dice and 6 possible numbers to come up. But notice, for example, there was no number that didn't appear at all. The least number here, the 4s, there were 6 4s, and the most number, the 3s, there were 15 3s. So there was certainly some variety around the number 10, but But nevertheless, our expectation was that on average, that we would expect a rather even distribution of these different numbers 1 through 6. We would not expect all of them to come out 6s. And as I say, this is a more extreme variation from the numbers than I usually get when I do this experiment. But that happens too. With probability, you get these kinds of variations. So the role of probability is to try to describe the operation of random occurrences in the aggregate. So one of the challenges for this course is to understand what to expect from randomness. And that is the role of probability, to describe what to expect from random phenomena. And the goal of probability is to give a numerical measure of those chances. So we're going to then see a myriad of applications, by the way, of probability in all sorts of things, from games to science to business and many other parts of life. Let me take just a few minutes to tell you how the whole course will be organized. In this lecture, besides this introduction, we're going to introduce the basic ideas of probability. And then in the next lecture, we're going to talk about the question of what is the nature of randomness. And this is going to be the lecture in which we're going to see some of the surprising issues that are associated with randomness. In lecture 3, we're going to introduce the concept of expected value. Expected value is a measure that using which we can make decisions about probabilistic kinds of outcomes. It gives us a numerical way to say whether or not to bet on this or that game or make this kind of an investment. In lecture 4, we're going to take a random walk. A random walk is a description of random fluctuations, and we'll see these appear in all sorts of application areas, such as physics and biology and finance. In lectures 5 and 6, we're going to see how probability plays a role first in the physical sciences, and then in lecture 6 in the biological sciences, in modern scientific descriptions of these scientific areas. And then in lecture 7, we're going to see how the world of finance is described using probabilistic models, and including models of stocks and option behaviors. And in lecture 8, we're going to talk about how probability appears where we don't expect it. So finding probability where we don't expect it. And there are all sorts of amazing areas that seem to have no random component to them at all, and yet where probability can play a central role. In lectures 9 and 10, we're going to discuss conditional probability and give some of these really famous examples that any course in probability must have, and they're just wonderfully interesting things to discuss, such as the birthday problem, for those of you who know that. But you can hear that in lecture 9 and 10. And then in lecture 11, we're going to look at probability from a different point of view, namely probability associated with measuring a level of belief instead of a measure of the frequency with which a random process occurs. This is the Bayesian view of probability. And then in the final lecture, we're going to see some examples that challenge our intuition about probability and then show once again how prevalent probability is in our world. But we're going to start today to introduce the very basics of probability by introducing it where the investigation of probability began historically, namely with gambling. Gambling presents us with all sorts of clear examples of randomness and of probabilistic analysis. And so that's where it started. That's where the mathematical investigation of probability first arose. It began in the 17th century when a gambler by the name of Antoine Gambeau, the Chevalier de Marais, sought the advice of two famous mathematicians of the day, Pierre Fermat and Blaise Pascal. And those two, Fermat and Pascal, developed the fundamentals of probability, although it had been discussed somewhat before. So let's begin with taking a die and explaining the most basic concept of probability. Remember, the concept is that we wish to associate a number, giving a numerical value, to a random process, to a process where there are several different possible outcomes, but we don't know which one will happen. In the case of a die, there are 6 sides to a die, of course, And consequently, we would say that the probability of any one of those arising is as equally likely to happen as any of the other sides arising as if we roll the dice. And consequently, we give a number to that by saying there is a 1 out of 6 chance that, for example, a 5 will arise if I roll a die. And consequently, that is the very most basic concept of probability. That if we have equally likely possible outcomes of some experiment or some trial, then we'll say that we just count how many outcomes there are that are equally likely, and then the chance of any one of them occurring is 1 over the number of outcomes that are possible. So in the case of a die, it's the probability of coming up a 4 is 1 out of 6. Okay. Now, by the way, what we're going to be discussing in the first part of these lectures is a field called discrete probability, where we're just talking about a finite number of the possible outcomes that can happen, and that will start to simplify our discussion, and then later we'll extend that to other realms. So, in the case of a die, there are 6 outcomes that are equally likely to occur. If I take another paradigm of probability, namely a coin, and I flip the coin, there are 2 equally likely outcomes that could occur, a head or a tail. Well, those possible outcomes are called outcomes, and if we have a collection of outcomes, such as, for example, asking the question, what's the probability of rolling a die and getting an even number, then that's called an event. And the collection of outcomes that are even is called an event, and I could ask, what is the probability of rolling an even number? And of course, to compute the probability of rolling a die and getting an even number, it's very simple. It's just, since there are 3 even numbers, 2, 4, 6, the probability is just 3 out of 6. Well, so these are the very most basic concepts of probability. And to summarize, let me just point out that probability has a couple features. One is that the probability of a particular outcome or of an event is equal to a number, and that number is always a number between 0 and 1. And the number 1 means that the event is definitely going to happen. So it would be like, what's the probability that I roll a die and I get some number? Well, it's going to happen. That's probability 1. And probability 0 means that the event will not happen. If I have just finitely many possibilities and I roll a die and I say the event is that nothing will come up, well, that's not going to happen. Probability 0. So if you look at all of the outcomes of a particular trial or experiment, and this could happen or that could happen or the other thing could happen, the probabilities, the sum of those probabilities of the different possible outcomes, if you list all of them, the sum has to be equal to 1, because the probability that something will happen is 1. So these are just some very basic things. The second one is, if you have the probability that an event has happened, for example, the probability that I roll a 5 if I roll a die is 1 out of 6. So the probability of the event of not rolling a 5, that is everything else, is going to be 1 minus a 6th, or 5/6. So these are some basic things, and as we come to them in actually computing things, we'll refer to them again. But these are some basics of probability. And I would say that this next equation is one that summarizes the basics of probability most clearly. And that is that if we have a collection of outcomes that are equally likely, and we want to compute the probability of a particular event E, and remember, an event is just some set of those outcomes, then the probability is just a fraction. And the denominator of the fraction is the total number of outcomes, and the numerator of the fraction is the number of outcomes that are in the event. So as I said before, if I want to say, what's the probability of rolling an even number? Well, there are 3 even numbers, so that's the numerator, and then there are 6 possible outcomes, 1 through 6, so the probability of rolling an even number is 3 out of 6. Now, so what that tells us is that probability for cases where there are where there are an even number of outcomes, I mean, where every outcome is equally likely to occur, the question of probability is a very simple question because it's just a question of counting. You count how many things you're talking about in the event you're trying to describe and divide by the total number of outcomes that are possible. Very simple. The only problem is that counting is anything but simple. It turns out that counting is one of the hardest things that we can do. And let me just demonstrate this by talking about an example that is very common to think about in probability, namely talking about cards. So here I have a deck of cards. Now, if we deal out a poker hand consists of 5 cards. And so we can ask questions about the probability of getting various poker hands. Now, so let's go ahead and be specific here and think about a particular poker hand that we would like to get and see if we can compute the probability of getting it. What's the probability of getting a poker hand that has all 4 aces? So now this is what you'd like. If you're sitting at a poker table and somebody dealt you the following hand, you'd be very happy because there are 4 aces there. Well, remember, the concept of probability and computing the probability is to count the number of outcomes that we're interested in, namely those hands that have 4 aces, and find out how many there are among all possible ways of being dealt 5 cards, how many of them will contain 4 aces. And then all we do is we divide by the total number of 5-card hands you could be dealt. Well, so all we need to do is count 2 things. Well, let's go ahead and start by counting the easier one first. The easier one to count is the number of hands that contain 4 aces. The reason that this is an easier thing to count is because if 4 of the 5 cards in a randomly dealt hand are aces, there's only 1 card remaining. But that 1 card could be any one of the remaining cards in the deck. It could be the Queen of Hearts, it could be the 4 of Clubs, it could be the 6 of Hearts, it could be the 7 of Spades, it could be any of the remaining cards in the deck. How many remaining cards are there in a deck of 52 cards if 4 of the cards in the hand are already aces? Well, the answer is there are only 48 remaining cards. So that means among all the possible ways of getting 5 cards, there are only 48 ways of getting 5 cards that contain 4 aces. It just depends on that last card. Okay, so we've done, half of our counting is done. We've counted how many outcomes have 4 aces in them. Total 48. Now all we need to do is talk about the denominator of our fraction. Remember, to compute the probability, we want to compute the number of hands that contain 4 aces divided by the total number of 5-card hands that could be dealt. Well, how in the world are we going to count how many possible 5-card hands there are total if you were just dealt a deck in a deck of cards that you were dealt 5 cards? How would you compute such a thing? This is a difficult question. So let's go ahead and figure out how to do it. And the way we do it is we analyze it in the following way. We say to ourselves, okay, let's imagine that we're being dealt these cards one at a time. So the first card that we're dealt is something. In this case, it's the 5 of Clubs. So we're dealt the 5 of Clubs, and then we say to ourselves, aha, after being dealt the 5 of Clubs, how many cards could appear as the second card in the hand that we're being dealt? Well, it could be any one of the remaining 51 remaining cards in the deck. So any one of these 51 different cards could be the second card that we're dealt. Now, for any one of those choices, for example, this 2 of Hearts here, choice, for any one of these choices, of these being the first 2 cards, how many choices are there for the third card? Well, let's see. It could be anything that we can imagine. Like it could be the King of Diamonds, 6 of Spades. It could be any of these things. How many are left to be chosen from? Well, if you've already picked 2 cards, there are 50 remaining cards. So here in this graphic, we can see this bifurcating tree of possibilities. For every first card, There were 51 possible second cards. After choosing the first two cards, there are 50 possible third cards, there are 49 possible fourth cards, and there are 48 possible fifth cards possibly dealt to you as a hand. Are we correct then in saying that the total number of 5-card hands we could be dealt, which is 5 are the number of hands, cards in a standard poker hand, 52 times 51 times 50 times 49 times 48, is that the correct answer for the number of hands that we could be dealt? By the way, that number, if we actually multiply it out, is 311,875,200. There are a lot of different ways to get 5 cards in order. But is this a correct count? Counting is tricky. And the reason that it's tricky is because this would not be a correct count for the number of 5-card hands you can get. And the reason is that look at this hand that we've just counted. This was one of the hands we counted. The 5 of clubs, 2 of hearts, 8 of diamonds, king of diamonds, 7 of clubs. That was one of these 311 million something hands that we counted. But notice that if we just change the order and we put the 2 of hearts first and then the 5 of clubs and the other 3 cards, we would have counted that as a different way of getting 5 cards, right? Because this one started with the 2 of hearts, so it's different from the one that we counted starting with the 5 of clubs. But nevertheless, this is the same poker hand. When you have a hand of cards, you can move them around. It doesn't matter. And consequently, we've counted this same hand, these same cards, many, many times. We counted this ordering as a different thing from this ordering, as a different thing from this ordering, as a different thing from this ordering. Every possible ordering has been counted separately, and yet it's the same hand. So what we need to do is think about how to systematically count how many times we have overcounted. And the answer is that we have overcounted by the number of ways we can take the same 5 cards and reorder them. Well, we could put any of the cards first, any of the 4 remaining cards second, any of the 3 remaining cards third, any of the 2 remaining cards last, and then the last card is determined. So we have a total of 5 times 4 times 3 times 2 times 1 different ways of counting the same 5 cards that we have overcounted by. So to get the actual number of hands possible in poker, it's 2,598,960 because we take the 311,875,200 of hands that count the order in which we get them and divide by the fact that each hand has been counted 120 different times. Now, this, by the way, is the area of combinatorics. How to carefully count such things as this is a whole area of mathematics called combinatorics. Having explained all this thing, I hope that you forget it, because I want you to focus on the bottom line of what we're talking about, namely that to compute probability, we need to count the total number of hands with, in this case, 4 aces, and divide by the total number of hands to get the probability. That the thing to keep your eye on is that probability is just the total number in the event divided by the total number of possible outcomes. Let's talk about what's the probability of getting a straight? A straight is where the cards are in order, like 3, 4, 5, 6, 7, 8, but 3, 4, 5, 6, 7, but they can be in any suits. Well, once again, it's a matter of counting. By careful counting, and it's tricky, you can count that there are 10,200 poker hands that are straights. So the probability of getting a straight is that 10,200 divided by 2,598,960, which we already computed, was the total number of poker hands that you can get, for a probability of 0.004. We can do the same thing to compute the probability of getting a flush. A flush is a hand where all of 5 cards are in the same suit. The number of poker hands that are a flush are 5,108, it turns out, by careful counting. So the probability of getting a hand, if just being dealt 5 cards, where all of them are the same suit, is only 0.002. That is 2 out of 1,000. So if we want to, and by the way, there's a technicality for both straights and flushes, is that something that's both a straight and a flush is not counted as a straight, nor is it counted as a flush. It's a different category. So that's why if you try to do this at home, you'll probably get a slightly different answer. The point is that we've just computed that the probability of being dealt 5 cards that are a straight is 4 out of 1,000, and the probability of getting 5 cards where all the cards are in the same suit is only 2 out of 1,000. The way poker works is that the rarer the hand, the higher the value. So a flush beats a straight at poker. Okay, so to conclude this lecture then, I want you to focus on one thing, namely that the basics of probability are that if you have an experiment or a trial, such as being dealt 5 cards from a deck of cards or rolling a die, if you're doing a trial which has equally likely outcomes, then if you want to compute the probability of some event, all you do is you count the number of outcomes in the event, such as the number of straights, and divide by the total number of outcomes that there are, such as the number of hands that could possibly be dealt. And that fraction is the probability of that event. In the next lecture, what we're going to do is to take up the challenge of trying to understand the nature of randomness itself. I look forward to seeing you then.